Problem number 7, example 2.8. This is a case for doubly reinforced concrete beam. The problem states, compute the bending stresses in the beam shown where N is 10 and M is 118 kip-foot. This is the section of the beam. We have steel below, which is for tension, and we also have steel above, which is for compression. Let us account now for the given. We have the beam width, this is 14 inches. The height of the beam, 20 inches. The effective depth, D, the distance from the outermost compression fiber, which is here, to the centroid of the tension steel. So this is your D. And that is 20 inches minus 2.5, because 2.5 here, or 2 1/2, is measured from the bottom to the centroid of this tension steel. So this one is your D, and this is equal to 17.5. Next is the location of your compression steel. Let's designate this one as D prime. So this is the location of it. It is also the distance from the outermost compression fiber to the centroid of the compression steel. So here we have, this is given to be 2.5 inches. Then we have the modular ratio. Then area of steel. For tension, we have 4 pieces of number 9. And if you try to calculate it, the area is 1 square inch for 1. And then since there are 4 pieces, so that will be 4 square inches. Then for the compression part, we designate this one as AS prime. It has 2 pieces of number 9, so 2 square inches. And moment is 118 kip-foot. It's here. So we are to compute for the bending stresses. So as you know, bending stress is MC over I. So we need the C and we need the I. And our C is the location of the outermost compression fiber to the neutral axis. So therefore, the first step here in our solution is to solve for the location of the neutral axis. Alright? So here, this is our neutral axis. And the distance from the neutral axis to the outermost compression fiber is designated as X. So this is the unknown X. And in Microsoft Excel, the way I solve it is in a tabular manner, and I use shift solve or goal seek to solve for X. If you do it manually, you can also equate and then find the unknown, one equation, or one variable, one unknown equation. So you can easily solve it using the shift solve in your calculator. So let's now fill out this table. A1, this is your area 1. And this is the concrete part. Let me shade it for emphasis. Area 1 has a width of 14 inches. And it has a height of X. Alright? So, I refer to this cell. Okay? Then, area is simply base times height. And Y is the distance from the centroid of this area to the neutral axis. So this distance. And this is simply X over 2. So X over 2 equals this value here, the C20 cell, over 2. Okay, and your AY is the product of this cell and this cell. Okay, now for AS, we don't have width and height because these are circular, circular in shape. So therefore we don't have B and H, we only have the area. So area is 4, but don't forget, to get the transformed area of AS, multiply it with the modular ratio. So I will multiply it with this value here, n, and we get this value. And then my y is this distance here from the neutral axis to the centroid of the tension steel. So this distance is 17.5 minus x. Okay, because your d is 17.5, then deduct x, then you will get this, the value for this portion. So 17.5, I refer to this cell, minus x, or this cell. Okay, and lastly, we have for the compression steel designated as AS prime. Now take note of this: to get the transformed area of AS prime, multiply it with 2n minus 1. Okay, for tension steel, multiply it with n, but for compression steel, multiply it with 2n minus 1. So this one, the 2 square inches AS, shall be multiplied by 2n, 2 times n, or this value, minus 1. Okay, take note of this, 2n minus 1. And the y is this value here, and that is x minus 2.5. So equals x minus 2.5, or here. Okay, then after that, you have to equate the tension and compression, no? For the compression, it will be on the left side of the equation. For the tension, it will be on the right side of the equation, so that the equation will be like this: area 1 y1 plus compression steel AS prime y, let's say y2, equals AS y, no, this is y3, no, y3, and then AS, then y2. Okay, this one is the tension steel, this one is the compression steel. So if you try to transfer to the other side to make 0 the right side, so you will get this A1 y1 minus AS y2 plus AS prime y3, that's equal to 0. And then this one, we plug it in here, equals this value minus the second value plus the third value, equals 0, supposedly. Okay, but since we did not input the value for x yet, then this will have a different value. So now we use the goal-seek function. Go to data, what if analysis, and goal-seek. So set this cell to value 0 by changing this cell. Okay, so after a few clicks, Microsoft Excel was able to find X, and this is 6.45. In your calculator, you can encode all the parameters here and then shift solve. Now, and then the unknown value will be given. Okay? So now that we have the location of the neutral axis, we can therefore solve for I. Okay, just copy this one. For the B, 14. For the H, now we X is already found out, so H is 6.45. And the IO is BH cubed over 12. BH cubed over 12. Okay? And the area, of course, is B times H. And our Y is X over 2, as you can see here. And then this one is found out already here, so we can just refer to this cell. Then IO plus AY squared. Okay? Because when you solve for I, if you solve for I, that will be the summation of all the IOs for all the sections, whether steel, concrete, then area times D or Y squared. Okay? So like that. So we are going to sum up all of the IO plus AD squared. Now, for steel, always remember that IO is not calculated because it is assumed that steel has no stiffness. So, here, for the area, we still use the 2n minus 1. Not 2n minus 1. And then for this, we use the n. Okay? Or rather, for AS, for tension steel, we have n. And then for AS prime, we have 2n minus 1. Okay? Then for Y, just copy all the values above. And then IO plus AD squared. This one. Then after that, you add the 3 values and you generate this I. So to summarize, we already have the 3 values for Y to be used for the moment for the bending stress equation, which is MC over I. Okay, this C will be either Y of concrete or Y of steel or Y of compression steel. Okay? So we have to solve for the 3. For the concrete, for the steel, and for the compression steel. So that's why we have all these values here. So Y of concrete is this value here. And then Y of steel, for the tension, we have this value here. And then Y of compression steel, we have this value here. Okay? Then, after generating these values, we can now plug into the MC over I equation. So, for concrete, the moment is 118 and always multiply it with 12,000 to get pound and inch unit. So, that will be 118 times 12,000 times Y of concrete over this I. And you will get this value. For the bending stress in steel, Fs, this is for tension steel, still use the MC over I or My steel over I, but you have this value here, the N. Okay? So that will be 10 because N is 10 times 118 and multiply it by 12,000, and then the Y of steel is 11.05, then divide it by the value of I. You will get this value. Then for Fs prime, there's a note here: in solving for bending stress of Fs prime or compression steel, multiply it with 2 times the modular ratio. So that's why we have here 2n times m times Y of steel over I. So 2n, 2 times 10, because n is 10, times moment, which is 118, times Y of steel, but this one is compression steel. Let me just emphasize, Y steel compression, which is 3.95 over the same I here, and you will get this value. And if you can see this diagram, this is now the transformed area. Okay, you can see here that because of N, the area of steel became larger, and the area of compression steel also became larger. Okay, that's how you convert. It's like converting steel to concrete. So you will have a greater area, a bigger area as compared to the concrete. Okay, thank you very much.